S1 equals AB, S2 equals EI, DBA, OOO. Does S2 contain a permutation of S1? Most people reach for recursion here or brute force. Both time out on LeetCode. There is a 16-line solution that runs in O of n and it uses a pattern you might already know. Hey everyone, welcome back. If you are new here, hi. This is the sliding window series, one pattern at a time. No rushing, no skipping steps. Today is episode 5. That puzzle I just showed you, that's what we are solving today. And I am not going to explain it yet. I want you to sit with it for a minute. S1 is AB, S2 is EI, DB, A, OOO. Does S2 contain any permutation of S1? Pause if you want. Actually think about it. I will wait. The answer is true. BA, B and A is sitting right there inside S2. Index 3 and 4. BA is just AB rearranged. Same characters, same counts, different order. That's a permutation. Output equals true. Now, how do you find that for a string that is not 8 characters but 100,000? That's the question. And by the end of this video, you will know exactly how and why. Let's build it. Let me make the problem completely clear before we touch any code. I always say this and I mean it. If the problem is not clear, the solution won't make any sense. So let's spend a minute here. We have two strings, S1 and S2. The question is simple. Does S2 contain any permutation of S1? So what is a permutation? It's just a rearrangement. All the same characters, all the same counts, any order. AB and BA, both permutations of each other. ABC, BCA, CAB, all permutations of the same three characters. It's like having the same letters on scrabbled tiles and arranging them differently. 3 examples on the slide. Let me walk through each one. Example 1. S1 is AB, S2 is EI, DBA, OOO. Output is true. Why? Because look at S2. EI, DBA, OOO. Index 3 and index 4. BA. Same characters as AB. That's a permutation hiding inside S2. Example 2. S1 is AB, S2 is EIDBO, AOO. Output is false. This one is sneaky. The B and A are both in S2, but they are never together in a 2-character window. They are always separated. So no permutation of AB exists as a contiguous substring. Example 3. S1 is A, S2 is A. Output is true. The simplest case. The whole string is the only window and it matches. Now before I go to the next slide, I want you to sit with one question. What should the window size be? Hint is on the slide. It relates to the length of S1. Think about why that has to be true. I will answer it on the next slide. But if you are thinking the window has to be exactly length of S1, you are already halfway there. This is my favorite slide in the whole deck because once this clicks, the entire solution becomes obvious. Here is the insight. A permutation uses all characters of S1, exactly, every single one, once. So what does that tell us about the window size? The window has to be exactly length of S1 characters long, not bigger. If the window is bigger than S1, it has extra characters that S1 does not have. That cannot be a permutation of S1. A permutation uses exactly the characters of S1, nothing extra, not smaller. If it is smaller, it's missing some characters from S1. So also not a permutation. So the window size is locked. From the moment we start, we know it. We never change it. We just slide it, one step at a time, from left to right. Window size is locked. Only slide, never shrink, never expand. So how is this different from episode 3? In episode 3, longest substring without repeating characters, the window was variable. It expanded when a new unique character came in. It shrank when a duplicate appeared. The size was always changing. Here, the size is fixed from the start. There is no expanding, no shrinking, just sliding. Look at this table, episode 3 versus episode 5. Episode 3 used a set. We cared about whether a character was present or not. Binary, yes or no. Episode 5 uses a counter. We care about how many of each character. Frequency, not just presence. That is the data structure shift. Set to counter. And that one change is why the window behavior is completely different. Same pattern family, different personality. Alright, 4 steps. Let me walk through each one carefully. Don't rush this slide. Each step builds on the previous one. If one step does not make sense, the code won't make sense either. Step 1. Build frequency maps. Two counters. One for S1. This is our target. It never changes for the entire run. The second one is for the initial window. The first length of S1 character of S2. This one will change as we slide. Think of count S1 as the answer key and window as the student's current answer. We are going to keep checking if the student's answer matches the key. Step 2. Check the first window. Before we even start the loop, check if window 0 is already a match. A lot of people skip this step and then they get a wrong answer on edge cases where S1 equals S2 or where the match is at the very beginning. Always check window 0 before the loop. One line, don't skip it. Step 3. Slide the window. This is the heart of the algorithm. One character enters from the right. One character leaves from the left. Window moves one step forward. Why do we delete the key when the count hits 0? Because if we leave A with 0 count in the counter, it won't equal a counter that does not have A at all. Because in Python, A with 0 count and a empty map are completely different. If we don't clean up 0 counts, our comparison will fail even when it should succeed. So this delete line is not optional, it's critical. Step 4. Check at each position. After every single slide, compare the window counter to the S1 counter. If they match at any point, return true. Finish the whole string with no match, return false. 4 steps. That's the complete algorithm. A fixed window slides from left to right. At every position, we check if the character counts match. That's it. Now I want to prove this actually works. Not just explain it, prove it. We are going to run through every single step manually. S1 is AB, S2 is EIDBAOOO. Expected answer? True. Our target counter, count S1 equals A with 1 count and B with 1 count. This is fixed. This never changes. Window size is 2 because length of S1 is 2. Step 1. L is 0, R is 1. Window is EI. Window frequency is E with 1 count and I with 1 count. Does E1 I1 map equals A1 and B1? No. Slide. Step 2. L is 1, R is 2. Window is ID. Window frequency is I with 1 count and D with 1 count. Match? No. Slide. Step 3. L is 2, R is 3. Window is DB. Window frequency is D with 1 count and B with 1 count. Match? No. Slide. Now step 4. L is 3, R is 4. Window is BA. Window frequency is B with 1 count and A with 1 count. Does B1 and A1 equals A1 and B1? Yes. return true. Found it. 4 steps. Now look at the visual. Watch the window slide. The window just moved forward, one step at a time, never went back. And why is this O of n? Because every character in S2 entered the window exactly once and left the window exactly once. Each character was touched at most twice across the entire run. The window never goes backwards. That's the guarantee. Here is the full solution. Let me read it line by line, not just show it. First line, the guard clause. If S1 is longer than S2, a window of size length of S1 can't even fit inside S2. Return false immediately. No computation needed. Always write this guard. It costs you nothing and it saves you from edge cases that trip up your whole algorithm. Now two counters. Count S1 is fixed, the target. Window starts as the first length of S1 characters of S2. This one changes every step. Check window 0 before the loop. Don't skip it. The slide loop. R starts at K, one position past the initial window and moves to the end of S2. R minus K is the left edge, always exactly K position behind R. So as R moves right, the left edge moves right too. Fixed size window sliding forward. I stored left char and right char as variables first. I didn't have to. I could have written S2 of R minus K directly, but writing it twice in 4 lines is error prone. Naming it once makes the code read like what it's doing. Add the new right character, remove the old left character. If a count drops to 0, delete that key. Now check after every slide. Any match, return true immediately. If loop ends with no match, return false. Read it top to bottom one more time in your head. Guard, two counters, window 0 check, slide, add right, remove left, clean zeros. Check each position, return false if nothing found. 16 lines, one pass, O of n. I could just say it works and move on, but I always feel better when I actually see it run. So let me jump over to LeetCode right now. We will type this exact solution, run the test cases, and we'll check some edge cases. LeetCode 567 Permutation in string. Same problem we have been working through. Two strings S1 and S2. Return true if S2 contains a permutation of S1 or false otherwise. The examples, same ones we covered. AB in EIDBAOOO, true. AB in EIDBOAOO, false. Medium difficulty. After what we just built, this should feel very manageable. So LeetCode gives us the class and method signature already. We will write everything inside this. We need counter for both frequency maps. So I am adding the import at the top. Guard clause first. S1 longer than S2? Impossible. So we will return false immediately. Now we will declare our two frequency maps. One initial window counter, count S1, target counter, window. Now we will do window 0 check before the loop, always. So if window 0 is equal to count S1, then we will return true there itself. K is the window size. Now we will run the loop one past the initial window till the end of the string. Now we will declare the left char and right char, where left char will start at S2 of R minus K and right char will be S2 of R. Now we will add right and we will remove left and we will clean up the 0 counts. So our counter stays accurate for comparisons. Now we will do the check. Check if the count S1 is equal to window. Then we will return true. So we will do this check after every slide. Now after the loop is finished, we will return false if there is no match. There it is. The guard clause, two counters, window 0 check, slide, add right, remove left and clean zeros. Then check each position and return false. Now we will run the test cases. All test cases passed. Let me test the edge case where S1 is ABC and S2 is AB. So basically length of S1 is greater than S2. Since S1 is longer than S2, it should be false. See, the output is false and the test case passed. It is caught immediately by the guard clause. Now we will check a frequency case where S1 is AAB and S2 is AAAB. Does AAAB contain a window with exactly 2 A's and 1 B? True. Window at index 0 to 2, A2 and B1 matches exactly. Let's run it. It should return true. See, the answer is true. So if you had used a set instead of a counter, you would only check if A and B are present. They are. So a set-based solution returns true for almost anything. Wrong. The counter catches it because it checks exact counts. Now let's submit the solution. Accepted. Runtime in the top percentile, which makes sense for O of n. Now before we go back, one thing. 16 lines, one input, no recursion, no generating permutations, no sorting. Why is it this clean? Because of what we figured out on slide 3. The window size is fixed. Once you know that, the rest follows naturally. The data structure, the slide mechanism, the comparison. All of it comes from that one insight. If you would try to solve this by generating permutations, and a lot of people do, you would get factorial time complexity. It would not just be slow, it would time out. The constraints are designed to reject brute force. This is why the insight comes before the code. Always. Let's go back and talk about exactly why this is O of n. Because it's fast is not a good enough answer in an interview. You need to explain it. We just saw it pass. Now let's understand why it's fast. 3 things. Time complexity, how it achieves it, space complexity. Let's go. Brute force. Every window you extract, sort and compare. Fresh from scratch. Look at the string. Window 1 checks E and I. Window 2 checks I and D. You just rechecked I. You already knew that character. You threw it away and started over. Do that for every position in S2. That repeated work is exactly what makes it O of n cross m. Our approach. Same string, one pass. Watch what happens when the window slides. E exits, I stays, D enters. One remove, one add. I was already in the counter. We didn't touch it again. Every character enters the window exactly once, exits the window exactly once. 2 touches total across the entire string. That's O of n. Space. Look at the counter. Window 1, 2 keys, E and I. Window 2, 2 keys, I and D. It never grows. S2 could be 10,000 characters long. The counter still has 2 keys because the window size is fixed. And since the problem guarantees only lowercase letters, that's 26 maximum. Ever. Constant space. O of 1. The window never goes back. Enter once, exit once. That's the whole argument. 3 edge cases. These are the ones that cost people points in interviews. Not because the algorithm is wrong, but because they did not handle the boundaries. Case 1, impossible. Length of S1 is greater than length of S2. Return false immediately. We already handled this with the guard clause, but I want you to understand it conceptually. A window of size length of S1 physically cannot fit inside a string that's shorter. There is nothing to check. One line, return false and move on. We just verified this on LeetCode. S1 ABC, S2 AB caught immediately. Case 2 direct match. S1 equals S2 or S1 is a single character. This gets caught naturally by the Windows 0 check before the loop even starts, but it's worth recognizing explicitly. If S1 and S2 are the same string, the only window is the whole string and it matches immediately. Case 3 frequency matters. S1 is AAB, S2 is AAAB. Output is true. This is the one that catches people. If you are using a set, you check if A and B are both in the window. They are. You return true. But that's wrong for many inputs where frequency does not match. If you are using a counter, you check A with 2 count and B with 1 count. The window AAB has exactly that. We just verified this on LeetCode too. Write this down. Stick it somewhere. Frequency, not just presence. That is the mantra for this entire problem family. Think in terms of window size plus character frequency. That's the frame. Everything else follows. Here it is, the template. If you leave this video with one thing, let it be this shape. Not the code for this specific problem, the shape of the solution. 3 parts. I will say them slowly. Part 1. Check init. Always check Windows 0 before entering the loop. This is not optional. Skipping it is the most common mistake on this problem. Part 2. Slide. One enters right, one exits the left. Clean up zeros. Check each. Compare full counters after every slide. That's it. Those 3 parts, check init, slide, check each. Where does this template appear again? Episode 6. Find all anagrams in string. Exact same template. The only change, instead of return true on the first match, you do result.append r minus k plus 1 to collect every matching position. One line change. Same structure underneath. Master this shape and episode 6 becomes a 10-minute video. I want to show you something before we wrap up. Look at this list. Episode 3 longest substring without repeating. Variable window set best. Episode 4 minimum window substring variable window frequency dict with formed counter. Episode 5 permutation in string. Fixed window counter comparison. Same family, same underlying idea. A window that moves through a string. But the condition changes. The data structure changes. The resize behavior changes. Episode 6 next. Find all anagrams. Same fixed window. One modification to what we built today. And coming further out, longest repeating character replacement. And max consecutive ones 3. Variable windows again, but with more complex conditions inside the loop. One template, 10 plus problems. That's the whole point of this series. You are not learning solutions. You are learning patterns and patterns transfer. Where we are. Episode 1 Intro to sliding window done. Episode 2 Fixed size window done. Episode 3 Variable size window done. Episode 4 Minimum window substring done. Episode 5 Permutation in string. That's today. You are right here. Episode 6 is next. Find all anagrams in string. Same fixed window template. One small twist. I will go deep on it. Episode 7 and 8 Variable windows with harder conditions. Those are in progress. If you have been following this from episode 1, I want to say something genuine. Most people who try to study DSA study by grinding problems. Randomly, 50 problems in 2 weeks and nothing sticks. What we are doing here is different. One pattern at a time. Deep understanding, full explanation of the why. It's slower upfront. but it's the only approach and that actually works when you are in an interview room and the camera is off and there is no Google. You are doing it right. Keep going. Alright, folks, that's episode 5. One sentence recap. Say it out loud after me. Fixed window, size equals length of S1, slide it, compare counters, and done. That's the whole thing. If this video helped you, hit like. I know everyone says that, but it genuinely makes a difference for how many people YouTube shows this to. If this helped you, there is someone else out there who needs the same thing. If something didn't click, drop it in the comments. I read every single one. If I see the same question from 5 people, that becomes its own video. And subscribe if you are not already. Episode 6 is already in progress. Find all anagrams in string. Same pattern, one twist. You will want to see it because it builds directly on what we just did today. Thanks for watching. Learn smart, code calmly. See you in the next one.